All right, so there are a lot of things happening. This is going to be standard for this department. So I've listed in a semi-chronological order events that are going on at least through Thursday this week. There are going to be 2 good colloquia this week in terms of topics for this course. The first today is on the continuum hypothesis, which we've talked about. And the second one on Wednesday is on the Banach-Tarski paradox. So if you want to get a homework exemption for one problem, if you go to both colloquia and write up a summary of both of them, I will give you an exemption from one homework problem. Okay? They are at 1 o'clock in Bronfman 106. And so it's nice to see that the material that we're doing is going to be expanded on and explained. So those are both worth doing. Okay, so today we're going to start combinatorics. I'm going to do things a little bit differently this week. I hope you don't mind. There will be no written homework this week. Okay, I know, I apologize. What I will do instead is I will post some problems that you should learn how to code. I do not care what language you code in, but I want you to have skills in coding. Numerous students of mine have told me year after year after year, one of the most useful things they got out of this class was being kicked into learning how to code. It served them beautifully when they applied for jobs or when they started their jobs. I don't care what environment you use. I will probably use either Wednesday or Friday this week to give a lecture on how to code. I'll give some examples in Mathematica. Mathematica is not the greatest language. It's not the fastest, but it has a lot of very nice user-defined functions. It has a friendly interface. It has good graphics capabilities. Okay, you can use whatever you want. For those of you who are stats majors, what should you be using? Yeah, that's absolutely fine to use. Okay, any of the other ones you want to use as well, absolutely fine. But you need to learn how to do basic programming. I'm not talking about a 1,000-line code problem. I'm talking about if you want to calculate the probability of a certain deal, being able to quickly assign cards and count. If possible, you want to learn how to code efficiently. Have I mentioned the Sudoku trick yet? Okay, I did? Okay, so several people are nodding heads. Have I mentioned that in probability in 341? No? I'm seeing a mix. All right, so since I'm seeing a mixed, all right, it has been mentioned. Okay, so I'll just include it in an email. All right, so what I want to do is I want to start talking about binomial coefficients. And so these are going to be the building blocks of many different probabilities. We'll have probability distributions that arise from them. We will have a lot of discrete combinatorics coming from them. This is not a class in combinatorics, but we will do a significant amount of combinatorics. I've had students who've gone to the Budapest semesters in mathematics, and they've actually skipped out of the first course in combinatorics based on how much we do. There is a lot of material in Chapter 3 that's extremely similar. I'll try to do some representative problems. I'm not going to do all of them. If there are things you really want to see or you found unclear, let me know and I'll try to go through them. So the first is n factorial is the number of ways to arrange n objects when order matters. So think of it as you have to assign n people. You have n choices for the first person, and then you have n minus 1 choices for the second, so it's multiplicative and goes on and on and on. Okay? If I want to choose 3 from n, order matters, the answer is n times n minus 1 times n minus 2. I have n choices for the first, n minus 1 for the second, n minus 2 for the third. One of the most important things to learn in mathematics is how to do nothing. Okay? There are 2 ways to do nothing. Anybody know the 2 ways to do nothing? Yes? You can multiply by 1 or you can add 0. What is the log of 1? 0. There's actually really only one way to do nothing. They're actually equivalent in some sense. But depending on how the problem is formulated, you might want to do nothing in different ways. All right? I want to multiply by 1 to make this look a little bit more friendly. Any thoughts as to what I should multiply by? Yes? Okay, so I can't just multiply by n minus 3. You violated either the 13th, 14th, or 15th Amendment of not doing the same thing to both. Excellent. Divided by n minus 3 factorial. So I've now multiplied by 1. So I haven't changed anything. But now this is n factorial over n minus 3 factorial. Now, If I'm just doing a product of three things, I'm not really convinced that this is a savings. But if I'm doing a product of k things and k is arbitrary, then this is definitely better. It also leads to the next thing. I want to choose k from n. Order doesn't matter. So over here, whenever you say order matters, think of it as we're choosing a president, a vice president, and a secretary. The order matters. Think of this as we're choosing representatives. Is the president the same as the vice president? No. Anybody remember George Bush Sr.'s famous quip about the job of the vice president? You die, I fly. The vice president's job is to go to funerals and express the deepest sympathies of the United States of America, and is basically cut out of a lot of the power decisions. Here, we're talking about representatives. Representatives, they're all equal. It doesn't matter if you are chosen first, second, third, fourth. Now, if you look at this, we've chosen three people where order matters. How many ways is there to assign an ordering among these three people? So I've got three people. How many ways can I order them? Yes? 3 factorial. So if I want to remove the orderings, this set of three people is going to be counted 6 times. It's going to be counted 3 factorial times. Once with one person first, another second, another third, and then all the other combinations. If I only care about choosing them, and I don't care about the order in which they're chosen, I get to divide by 3 factorial. So the answer is going to be n factorial over n minus k factorial. This is the number of ways of choosing k people from n when order matters, and now I get to divide by k factorial. And that removes the ordering. This is such an important symbol, or a function, we give it the symbol n choose k, and you might remember from high school it's sometimes written as nck on calculators. Anybody remember this? And I think this one they would sometimes write as, I think, np3 on old calculators. Permutations and combinations. Okay? So there's a lot of different properties of these coefficients. So properties. So the first is n choose k is n choose n minus k. And again, for those of you who are in 377, there's just unfortunately an overlap in material in the beginning of the semester. They will differ. Can somebody give me one way to prove this? Yes?
I guess if you're choosing k from n, then you leave n minus k.
Okay, so you just gave the good proof. And the example I used for 377, what Dr. Seuss story? The Sneetches. How many of you read Dr. Seuss's story, The Sneetches? The Sneetches on the beaches. And there are 2 types of Sneetches. Those that have stars on their bellies and those that don't. Okay? So they end up having this machine that adds and removes stars. Okay? Imagine I'm choosing k people to get a star on their belly. That's the same as choosing n minus k people to be excluded from receiving a star on their belly. So this is a proof by story. Okay? I love proofs by story. Okay? The problem is figuring out the right story to tell. There's another way of proving this. It's just brute force. Just expand what this is, and then do the algebra. So you can do it by algebra, and you can do it by brute force. I'm sorry. Algebra, which is brute force, or you can do it by story. The story is more elegant, but it often requires you to be clever. Okay? How many of you have seen the binomial theorem before? Okay, we will be needing the binomial theorem this semester. So x plus y to the n is x to the, let's do it this way, is n choose 0, x to the n, plus n choose 1, x to the n minus 1, y, plus n choose n, y to the n. Or equivalently, it's the sum, k goes from 0 to n, of n choose k, x to the k, y to the n minus k, or the sum, k goes from 0 to n, of n choose k, x to the n minus k, y to the k. Depending on how you're writing things, sometimes one is a little bit more convenient than another. You might have seen something like this years ago when you were doing Calc 1 and you're taking the derivative of the function x to the n. And you wanted to expand out x plus h to the n. And you only needed enough of the binomial theorem to know that it starts x to the n plus n x to the n minus 1h. There's a couple of ways to prove this. The first is that this is reasonable. When I expand things out, what's the highest power of x I could have? Highest power of x is n. Highest power of y? N. And so I have n factors. And for some factors I choose an x, for some factors I choose a y. Well, since there are n factors, if I choose x k times, I choose y n minus k times. And so what I need to do is to find the coefficient of x to the k, y to the n minus k, I have to choose x k times. How many ways are there to do that? And choose k. So this is a nice combinatorial proof of the binomial theorem. Okay? You can also prove it by induction. You can prove x plus y to the n plus 1 is x plus y to the n times x plus y. And so now if we know what this is, we can expand, and we're going to see we're going to get combining terms. So if I now want to get the coefficient of x to the k plus 1, y to the n, I think plus 1 minus k, I would be combining an x from here, and you can play those games. And I'll leave that as a nice exercise for you to do, go through. This will lead to an interesting relation. It leads to n plus 1 choose k plus 1 is n choose k plus n choose k plus 1. Anybody recognize this relation other than those from 377? Okay, what relation is this? Okay. Where is this relation from? Yes?
Pascal's triangle.
Pascal's triangle. So 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1. Not my day. 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, and so on. Each number is the sum of the two above it, and you have ones going down along the outside. There's a lot of wonderful properties about this. And this is essentially the defining relation of Pascal's triangle. This row is the expansion of x plus y to the fourth. It's the coefficients we get when we expand. Okay? So the question is, how would we prove this relation? Well, one way we prove this relation is we use this expansion here and we prove by induction. Can anybody give me another way we could prove this relation? How else could we prove this? Yes? We could use brute force. Right? When in doubt, use brute force. Or at least do enough to convince yourself that if you absolutely needed to, you could make it work. I remember I was taking a complex analysis exam at Yale, and I had spent 2 or 3 pages doing a brute force calculation for a problem, and then I wrote, there must be a better way of doing this, and then 2 or 3 lines later, I'm done. And the professor wrote in the margin, it's about time you realize that, Steve. And he was absolutely right to write that. On an exam, there is no way he would give a problem that would require that much algebra to just keep plugging away, plugging away, plugging away. There's got to be a way to step back and see what's going on. Frequently, if you just care that the result is true and you only have to do it once, brute force is fine. But it doesn't give you a sense of why it's true. So sometime later in the semester, I will bring some props and talk about Morley's theorem, which is a great way to learn that brute force is not the way to go. It's from a bet I made in grad school. I want to do the story proof. Story proof. So n plus 1 choose k plus 1 is n choose k plus n choose k plus 1. So we can either do this with NFL commissioners or Williams and Amherst. People in 377 don't get to vote. What do people want to do? Williams and Amherst. So first loud voice typically wins. So there are n great Williams students. And there's one student from Amherst. I won't say what they are. Okay. I want to form a group of k plus 1 people. Okay? So I've got n students from Williams, 1 from Amherst, and I want to form a group of k plus 1 people. Can anybody tell me how many ways there are to do that? Yes?
You can have a group with an Amherst person, or
I want to form a group of k plus 1 people. I don't care who's in my group. I just care that I have k plus 1 people.
possibly you can form groups with one Amherst person and you have one Amherst person.
Right. Okay, so one way to look at this is I could say, case 1, I have the Amherst person. How many ways is there to choose one Amherst person? 1. There's a better way of saying 1. I want to choose one Amherst person from the set of 1 Amherst people. Yes? 1 choose 1. I really love overkill. All right? I choose 1 Amherst person. How many ways are there to choose k people from the n Williams students? And choose k. So this is all the ways to choose k plus 1 people where you have the Amherst person. What if I don't have the Amherst person? How many ways are there not to choose the Amherst student? No, not to choose the Amherst student. I want to not choose the Amherst student. Yes? It's 1 choose 0. There's one possible person from Amherst, and I don't take them. Now, I have the n students from Williams. How many must I take to get k plus 1 people? K plus 1. And so here is proof by story. Because this must be the same as I've just chosen k plus 1 people from n plus 1. So this is proof by story. Notice that the top adds up to n plus 1 in both cases, and the bottom adds up to k plus 1 in both places. This is why I like to be overkill and write the 1 choose 1 and the 1 choose 0. Do we really need to write this? No. But when you write it down, it makes it a little bit easier to see what's going on and to see how things are connected. As an example, a blast from the past, let's say f of x equals x to the n. What's f prime of x? Yes? nx to the n minus 1. Let's say now we have a of x is g of x to the n. What's a prime of x? Yes? Times g prime of x. So really, what should I multiply this by? Yes? dx over dx, x prime, 1. This is the special case when g of x equals x. There's really a times 1. Nobody writes times 1 over here. But it's good to remember that it's here, because then when you generalize to the power rule, you remember, yeah, I've got to remember that g prime of x. It is worthwhile to write far more than you need to make it easier to read and follow and remember. It will cut down on your missing key facts. Okay? Any questions so far? Let's do one more proof by story. I did not do the dancing problem in 377, right? The dancing problem, and men and women. Okay. Well, we'll phrase it. We have n from Williams, n from Amherst. And what I want to do is I want to study the sum k goes from 0 to n of n choose k squared. Okay? This is the same as the sum k goes from 0 to n of n choose k, n choose n minus k. Right? I'm just using one of the early properties of binomial coefficients. There's a way to answer this with a proof by story. Anybody know what this answer is? So I'll give you a hint. It's a binomial coefficient. And you should be able to figure out what binomial coefficient is by what we did for Pascal. Yes?
Well, we know that n, like, I don't know, so n minus k is the same as n k, so we just do the same.
Well, no, that's why I expanded out like this, because n choose n minus k is the same as n choose k. So this sum is the same as this, and this one has a really nice interpretation. So if you look at what we did for Pascal's triangle a moment ago, this should tell you what the top is, and this should tell you what the bottom is. What should my top be? 2n. Excellent. And what should the bottom be? N. Okay. It's okay to be using a questioning tone right now, but when we did Pascal, we noticed, look, we looked at all the ways we could have a top of n plus 1 and all the ways we could have a bottom of k plus 1. So over here, what are we doing? I want to find all the ways we can have a top of 2n and a bottom of n. But now over here, it's not all possible ways, because here these are being restricted to n. How can I view this? I have 2n people. And I'm going to choose n of them. How many ways are there to choose n people from 2n? Well, by definition, it's 2n choose n. If I choose n people, I have to have some number from Williams. Let's call that k. Well, if I have k from Williams and I have n total, how many do I have from Amherst? N minus k. And so as I sum over all possible values of k, this will have to be 2n choose n. So this is another proof by story. Proof by story is an extremely powerful technique. The problem, of course, is it requires you to figure out what the right story is. Okay? So this is a quick introduction to binomial coefficients. It's extremely important to become comfortable with them. Calculating binomial coefficients becomes hard when the n and the k get very large. Small values of n and k, no problem. But we might eventually need n or k to be over 100. For your calculators, if your calculators are somewhat old, they will overflow if you ask it to do 100 factorial. Okay. Some of you have much better calculators and they'll go beyond 100 factorial. So we'll need ways to approximate these numbers. We'll want ways to try to figure out how these things are going. Okay. Any questions on binomials? So this is going to be like a little hodgepodge of various topics to cover. We've got poker games to do. We've got tic-tac-toe. Any preference? Poker. Okay. So poker is one of the games you can actually win in Vegas because you can play against other people, not against the house. So you actually do have a chance in poker. One of the big things in poker is, are you playing with 5 cards? Are you playing with 7 cards? All these different rules. I'm not going to go into all of that. The order of hands is typically done by a correlation with their probability of happening. The more likely the hand is to happen, the less value it has. So one possibility is you have nothing. Another is you have exactly 1 pair, maybe 2 kings, and then maybe a queen, 3, and a 5. Or maybe you have 3 of a kind, 3 kings. Or maybe you have 2 pairs. Which is harder to do? 2 kings and 3 kings, or 2 pair? Well, it seems reasonable to think that having just 2 of a kind is going to be more likely than having 3 of a kind. But what about 3 of a kind versus 2 pair? Well, this is where we want to calculate probabilities. And you want to know how much more likely is one than another. Or if you're trying to fill up your poker hand, how likely is it for you to get that card you need to give you the flush or whatever? What do you think makes calculating probabilities a little bit harder in poker? Yes.
And without replacement.
So one is we deal without replacement, but there's something else, a twist in some poker hands. Yes.
Well, you don't know what everyone else has.
So when you don't know what everything else has, yes.
Relative to the pot.
Well, that's in terms of the monetary amount. So the real thing is whether or not there's wild cards and how many wild cards are there and what are the wild cards. So is it all the deuces are wild, or some people play one-eyed jacks and suicide kings are wild? And you can have all these different rules as to what's the wild card. And depending on what's wild, that will affect the probabilities. And now all of a sudden you could have 5 of a kind. How likely should that be? So you want to calculate various things. So we'll do some poker hands. So we'll always assume that we're having hands of 5. So how many ways are there to choose 5 cards from a deck of 52? 52 choose 5. So there's 52 choose 5 hands of 5 cards. Now one of the most important things to be careful about in probability is to either always have order or never have order. Do not do partly ordered, partly unordered. This is one of the most common mistakes. Decide which way you're doing the calculation. Okay? So over here, there are 52 choose 5 ways of choosing 5 cards from a deck of 52. And when I'm doing it like this, I'm saying, I don't care which order I get them. I just care which 5 cards do I have. Now when you're playing a game of poker, it might matter which order you get them, because that could affect how you bid, whether or not you stay in. Right now, I am just looking at which 5 cards do I have. And I might want to know what is the probability at least 1 king. Okay, so how would I calculate the probability of at least 1 king? Yes?
1 minus the probability of no king.
Good, so the easiest way is this is 1 minus the probability of no kings. Otherwise, I would have to calculate the probability of 1 king, 2 kings, 3 kings, 4 kings. And I would have to worry about some events being doubly counted. I could look at what's the probability I have the king of diamonds in my hand, the king of spades in my hand. Oh, I could also have the king of diamonds and the king of spades in my hand. I've double counted those. So for something like this, it's much easier to calculate the probability that there are no kings. So what is the probability that we have no kings? Well, what should we divide by? Yes? 52 choose 5. This is the number of hands of 5 cards. And now I want to look at how many of these hands have no kings. So how many hands have no kings of 5 cards?
48 choose 5?
I'm sorry?
48 choose 5?
48 choose 5. Excellent. Right? And so this would be the probability we have no kings. Because if I have no kings, then there are only 48 cards available to choose my 5 cards from. And now you just go through and you do the algebra. Okay? So this would be calculating the probability that we have at least 1 king. Okay? What if we wanted to do the probability that there were at least 2 kings? Yes?
Which whether there's no kings and not just 1 king and not no kings.
So we want to calculate the probability that there's at least 2 kings. It's 1 minus the probability that there's no kings, and then minus that there's just 1 king. So sometimes you want to calculate the probabilities of exactly one happening. So what is the probability just 1 king? Well, we will divide again by 52 choose 5. Yes?
Would it be 13 choose 1 times?
Okay, why 13 choose 1?
Because there are 13 numbers, and 1 out of 13 is a king.
Okay.
And then multiply it by 4 choose 1, because there are 4 different suits possible.
So that would give you 13 times 4 would be 52. Okay, so let's try to do this calculation. So you want 13 choose 1. We choose one of the numbers, and it's a specific number, it's the king. Then there's 4 suits for the king, so it's 4 choose 1. Now what do we do for the rest? We've got to choose 4 more cards.
Plus
It's probably going to be times.
times
Okay, 12 choose 4. And then probably 4.
Choose one to the fourth to the fourth to fourth.
Okay. This is not a bad thing to try. We choose the special number from the 13, and then there are 4 possible choices for it. Now over here, there's 12 numbers remaining. We don't choose any more kings. We choose 4 of them. Now one of the problems is, what if we choose one of the numbers multiple times? This is choosing 4 distinct numbers from 12. We could actually have 1 king and 4 threes. So it's very easy to mix count. One of the things that's a little bit hard about something like this is look at what the sums of the bottoms and the tops are. If possible, you like the sums to be nice and be coming up to 52, coming down to 5. This would be all the ways maybe to take exactly 1 king and have 4 distinct numbers that are not kings. And this would be maybe a subset of the answer. And then what we would have to do is then we would have to start going through all these different cases. Okay, so it's a good thing to try, but it's not going to work because it's not going to get the whole space. But this would be a lower bound. What I would say is we want to split the cards into 2 parts. There's the kings and the non-kings. Yes? So let's see what that would be. So we choose one of the 4 kings, and then we choose 4 of the remaining 48. The top adds up to 52, the bottom adds up to 5. This is a really nice quick trick to say that it's a reasonable thing that we're doing. And this would now give us the probability of just 1 king. Okay? Any questions about this? Here's a nice result. The probability exactly k of something is equal to the probability at least k minus the probability at least k plus 1. We're not going to really use this now, but I just want this on your radar screen for later in life, or at least later in the course. That sometimes we have a very easy way to calculate at least. And if we can calculate at least, we can actually pass from knowledge of at least to knowledge of exactly. Let's say I want to have exactly k. Well, if I have at least k, and I throw away all the ones that are at least k plus 1, then everything that's left over is exactly k. It's not always easier to do it like this. This is 2 calculations. Sometimes the more direct one is easier. You have to be aware of how things are set. Okay? There's a whole slew of examples we can do on poker hands and whatnot. Is there any poker hand or any of the combinations, any of the readings from class related to this that people want me to do on the board? Everybody's happy with this stuff for now. Okay, so it's a calculation you do once in your life if you're playing poker, and then you memorize the relative probabilities of the different things. Okay, let's go to Tic-Tac-Toe. Tic-Tac-Toe is a fun game. Well, okay, not the way we play it, but you can make Tic-Tac-Toe fun. And in fact, I think I have somebody who's going to be doing a colloquium on fun Tic-Tac-Toe. For the I'm sorry?
Tic-Tac-Toe, is it?
No,
Okay.
no. Tic-Tac-Toe is a cheesy game show.
Okay.
Speak.
There's a colloquium called that.
Yes. I mean, I think that's what we're using as the title.
Oh, yeah.
In honor of the game show.
Yeah, I was
Yes.
just talking about
Yes.
that.
Yes.
Okay, cool.
I almost did this for day 1. I've done this some years. How many of you have ever seen the game show called Whammy? In the old days, it was called Press Your Luck. And you see a little screen, big bucks, big bucks, big bucks, stop! Do you know the story of the guy who broke the show? So it's kind of sad what happened, but what he noticed is that the order in which the light went around the board was not random. And this was in the days of VCRs. He recorded a bunch of shows and he analyzed it and he figured it out. You can actually see him smiling before it stops. As he won over $100,000. He is in the early 80s. He smashed all records for maximum win on a game show. For years, they refused to air the show again. Your CBS in the end did say, okay, we do have to pay you. And then they had a real random number generator rather than a semi-random number generator. Anybody see the movie Pixels with what's it, Adam Sandler, Kevin James? We just watched that this weekend. And basically, it turns out that aliens are going to destroy the Earth using 1982 video games. And the salvation is people who actually detect patterns in old games. Things that are not random, but appear random, have enormous opportunities. There was a Canadian, either statistician or geologist, who noticed that one of the Canadian scratch lotteries was not random. And I don't know why, but he actually felt compelled to tell them this. And their response was to shrug him off. So he mailed them 20 scratch tickets and told them how to scratch them, and was right 19 out of 20 times, at which point they started talking to him. I would have gone to a high school. Oh, I'm sorry, this is being recorded. No, he did the right thing. That's absolutely the right thing. I would not have gone to a high school or middle school and trained the kids on how to scratch them and find ways to balance the school budget. But there are lots of things that seem random but are not, and you have the opportunity to take advantage. Now let's look at tic-tac-toe. I'm going to assume everybody knows you alternate playing X's and O's. First one to get 3 in a row wins. If you're playing an intelligent component, no one gets 3 in a row. I am the tic-tac-toe champion at the elementary school playground. I have yet to lose, although I have been tied once or twice. How many opening moves are there for tic-tac-toe? Yes? 3 up to symmetry. You can move in a corner, you can move in a middle, or you can move in a center. So when you're trying to analyze something, you really want to figure out what are you trying to analyze. There's a whole slew of paths. If you just consider the game without taking into account symmetry, there's 9 opening moves and 8 responses. So there's 72 games after the first 2 moves. If you use symmetry, there's only 12. So this makes it a lot easier to beat little, third graders. Okay? So there will be a colloquium talk on some ways to make this game more interesting. One of my favorite ways to make this game more interesting is you bid on how much you want to move. And whoever bids the highest gets to move next. And either that money goes to the banker or that money goes to the other person. And then it becomes an interesting game theory question as to how much is each move worth. Later in the semester, I'll probably give you the following coding problem. If you want, this is a great time to do it now. Let's say you have 2 idiots playing tic-tac-toe, and they completely move randomly, and they have no knowledge of 3 in a row, and they just choose squares. Okay? What's the probability that if 2 morons play tic-tac-toe, the game ends in a tie? Now, this is a nice coding problem to do. You can go through all the possibilities, or you could try to simulate. Just play a huge number of games of tic-tac-toe. And the more games you play, the closer that answer should be to the truth. This is the basis of a lot of statistical inference, that if we do something more and more times, we should get a better and better sense of what's really happening. So it's a very difficult problem sometimes to calculate a probability exactly, but to simulate it is very easy. Later in the semester, I might do a mental card trick. I need to know the class a little bit better before I do that to use my mental powers appropriately. To prove why this trick works about 80% of the time is extremely hard and involves young tableaus. But to just numerically simulate and guesstimate an answer, very, very easy. So I want you to be able to program at this level. So if I give you, play a game of random tic-tac-toe 1 billion times. You should be able to write a computer program to play 1 billion random games of tic-tac-toe and see how often does it end in a tie. All right, that's the level of coding I want you to have for this class. Okay. Anything else on tic-tac-toe right now? So really, this is a placeholder to just get you used to the idea of thinking about how you want to prune the spaces. There's lots of ways of doing the calculations. When we're trying to calculate probabilities, we can break things up into 72 possible cases with 9 opening moves, or we can break it up into 3 opening moves and use symmetry to help. All right. As an aside, I want to just do a quick calc review. How are people at calculus? So here's function, and here's the derivative. X cubed. 3x squared. Wonderful. X to the 5/4. And let's do x to the square root of 2. Square root of 2, x. Okay. The proofs of these three are very different. The proof of the first one is x plus h cubed is x cubed plus 3x squared h plus terms that either have an h squared or an h cubed. This is where we use the binomial theorem. We use it to expand out x plus h. And we can do this because we have an integer power. We can't use that same proof for x to the 5/4. What we do is we say, let's let g of x equal f of x to the 4th is going to be x to the 5th. So here, f of x is x to the 5/4. We now know how to take the derivative of x to the 5th. And now we take the derivative of g of x by using either the chain rule or the power rule. It's a different method of proof for a rational exponent. For the last one, what does it even mean to raise x to the root 2th power? The way we do this is we say g of x is equal to e to the root 2 natural log of x. And that's actually how you take the derivative of x to the root 2. Is you need to know things about the exponential function, the logarithm function, and the chain rule. It's worth getting a sense of how deep and how difficult mathematics is. These things are often glossed over. You ask a calc student, what's the derivative of x to the root 2? They'll say this. But they almost surely have not seen a proof of this. So I'm not sure how many of you have actually seen a proof of this in your class. Yes?
Does that imply that x raised to a transcendental number needs a different proof also?
Well, I mean, it would be the same proof as this. Right? I don't really need that root 2 is algebraic.
Okay.
And in fact, any number here works. And of course, this proof also gives you this as well. But I need, in some sense, some way to take the derivative of the exponential function. And so it's interesting to think, how difficult is something? Okay. I think the next one is derangements. Yes. So here's a fun one. So consider n people, rearrange. What is the probability at least one doesn't move? So I have n people. I want to reorder them. So for instance, maybe it's 1, 2, 3, 4, 5, 5, 2, 3, 1, 4, I think. So here I would have one person is in the same spot. So I might want to calculate what is the probability if I randomly order n people, I don't have the same person ever where they started. So what do you think the easiest way to calculate this will be? Okay, so then the question is, how do we calculate everyone moves? Yes.
One minus probability that no one moves.
Well, okay, I mean, that's what was just said. So 1 minus probability that no one moves. But how do you calculate the probability that no one moves? Yes.
First look at the probability of holding that spot still and then rearranging the other one.
So this is going to lead to inclusion exclusion. So we're going to look at all the ways where person 1 is fixed. And then we'll subtract that. But then that double counts all the times when people 1 and 2, 1 and 3, 1 and 4. So we have to add some of those back. So we're going to go alternate. We're going to go back and forth, back and forth, back and forth. We'll talk more about derangements on Wednesday or Friday. I'm not sure when we're doing the computer program. But I want to get this on your radar screen. I'm going to end with the following. So in 4th grade, my son got on the blackboard, the teacher wasn't expecting anyone to get this, the square root of 5 factorial. And I was proud that my son said it's about 10. I would have been proud if he had said it was about 11, but he at least knew what the factorial was, and he knew what that strange V-looking thing was outside. And so I was talking with his teacher about the factorial. Does anybody know what 5 factorial is? So, what's 5 factorial? 120. No! 5 factorial is actually larger than 5 factorial factorial. Mathematicians can define anything we want. The question is, when is it useful? Okay, you want to define things that will arise. We define 5. Has anybody seen the double factorial? Yes, and it is? It is 15. It is 5 times 3 times 1. 8 double factorial is 8 times 6 times 4 times 2. The double factorial is every other. It's not the factorial of the factorial. And the reason is the factorial of the factorial doesn't really arise in problems. The double factorial, every other, actually arises all the time. We will see it when we get to the moments of the Gaussian. And so what I'll do is I'll end today with an example of where the double factorial arises. So let's say you have 6 people split into 3 pairs of 2. And maybe I want to know what's the probability a given split happens. So maybe my people are named A, B, C, D, E, and F, because I have no originality. And I want to know what's the probability that A is paired with B, C is paired with D, E is paired with F. That would just be 1 over the number of pairings. What do you think the answer is? Just based on what's on the board. What do you think the answer involves? A double factorial, probably. So let's look at this. I've got 6 people. Let's choose A. A has to be paired with somebody. How many choices are there to pair A with? 5. So we have 5 ways to pair A with somebody. Now how many people are left? 4. I choose one of the remaining 4. How many ways are there to give them a friend? 3. Now there's only 2 people left. I choose one of the 2. How many ways are there to give them a friend? 1. And this is just 5 double factorial. You could also prove this by induction. And so if you know that 6 is 5 double factorial, if you have 8 people, you have 7 ways to form a pair involving A, and now you have 6 people left. It would be 5 double factorial. So the double factorial has a lot of combinatorial meaning. So right now, we're building up our notation, we're building up our language, we're building up the functions we're going to use. We're going to calculate probabilities of events. We need ways to assign. Probably the most basic way of counting the probability of an event is you see how many times does it happen out of the number of candidates. And that fraction is the probability. So all that we're doing right now is we're looking at ways to count how many ways something happens. And that's why we're doing all this. Yes? You could. So what would you say the triple factorial should be?
Like every 3.
Yes, and the triple factorial should be every 3. And
But it is a trio.
yes. Well, but now if you try to split into trios, it's not going to be the triple factorial. So as a nice exercise, I'll give extra credit. Is there a nice formula for splitting 6 people into, well, okay, 6 people is not so bad, into splitting 3k people into k triples? Is there a nice formula for that, and does it involve the triple factorial? I wouldn't be surprised if it involved a triple factorial and maybe some other stuff as well. So there are frequently interesting formulas. There's interesting formulas for the double factorial in terms of the factorial. What does this seem to be missing? When you look at this, what numbers is it missing? I'm sorry, 2, 4, and 6, right? So I wasn't planning on doing this today, but we have 2, 4, and 6. Okay? What number divides 2, 4, and 6? 2. So I have a 2 cubed and then a 3 factorial. So if I look at 5 double factorial, I should be able to do this on the spot. So 5 double factorial, let me multiply by 6 times 4 times 2 over 6 times 4 times 2. Now what does the top become? 6 factorial, and the bottom is 2 cubed times 3 factorial. So there's probably a really nice formula for the double factorial in terms of the factorial. And in fact, this might even be a homework problem later in the semester, so you might have just gotten a big advantage. But there's really nice combinatorial stories to a lot of these. The goal is to find those stories, right? And then the other thing is to just keep seeing what we need to do to make everything rigorous. So we need to make calculus rigorous. And this is why I think a few moments ago over here on the board, we had all the different derivatives and what do you need. These combinatorics, that's how we calculate the derivative of x to the n, but to go beyond that, we need more. All right, this is a good place to stop.